So good afternoon, everyone. Today we have next Tutte Colloquium, and we have a pleasure to listen to the talk by Professor Carla Groenland. And Professor Groenland made her master's thesis at CWI and then a PhD at the University of Oxford, and then was a postdoc for a short time at the University of Utrecht, and then Marie Curie Fellow, I guess, also at the University of Utrecht, if I'm not mistaken. And then professor at the same university, and then now she works at Delft, TU Delft. Right. Yeah. So please welcome Professor Groenland.
Yeah, thanks a lot, and very impressively remembered all those random facts. So yeah, I'm going to talk about some problem about reconstructing graph from distance queries, and this is all joint work together with my PhD student Paul Bastide, so you can see a little picture of him here, and I just wanted to advertise him as well. He's very nice to work with, and he will also be on the postdoc market soon. So what we'll be thinking about is the following kind of setup. You could imagine that we have a computer network. We know the names of all the computers, but we don't know how they're connected. So they might be sending messages to each other, but the messages might not go directly. So maybe it takes 3 steps to send this message, and it goes via another sort of range of computers. And our goal will be to find out these interconnections, which we call the edges of the graph. And as you can see, the only thing we learn is just that the time that it took to send the message. So maybe it sends a message and it measures how long the message gets received back, but it doesn't receive the sort of full path information. So if we do this into a graph problem, we do this kind of query and we learn the number 3. So we don't know what has gone on. So either of these 2 options could have happened. There's a variety of other options that could have happened. But this is the kind of information that we learn. And by asking these kinds of queries, we want to, with as little questions as possible, find out the edge set of the graph. That is reconstruction from distance queries. So just to note that if we heard the answer 1, then of course we do know the edge is present. But in any other case, we don't directly learn. We just learn the edge is not present. We don't directly learn which edges are there. Okay, so through the talk, there will always be considering at connected graphs, just so that this distance function makes sense. We know the vertex set, which I will call V, and the edge set E is unknown. That's what we want to reconstruct. We have this kind of oracle. We get 2 vertices, and we get the distance. So as you just saw in the picture, and it will just be the length of the shortest path. We always assume our messages get sent in the most efficient way possible. These oracles, they're assumed to be adaptive. So we can ask a question, we hear the distance, now we can think of what question we want to do next, and the next query is allowed to depend on the answer that we just heard. And we say that the graph is reconstructed if there's no other edge set which is compatible with the answers we just heard. So we might receive a collection of answers for which there's only one edge set that could have given this set of answers. Okay. So just to make sure that you all understand, suppose now that we have 3 vertices, how many possible edge sets should I be considering from the start? 4, yeah, very good. So just to make sure that everyone understands, we're not considering this as isomorphism classes, we really have 4 different edge sets so far to consider. Okay, so now when we talk about the query complexity, when we have an algorithm, it's kind of a decision tree. We ask a question, we hear a response, we can ask a new question, etc. And the query complexity is now on the worst case input. So if we would, for example, want to reconstruct starting from all possible vertex graphs, we run the algorithm, all these different graphs, and we look at how many questions it takes to reconstruct it, and that's the query complexity. So just as a little example here, if suppose we had our 3 vertex graphs, we can first ask the distance between the first 2 vertices. If we hear the distance 2, we know which graph it is. Otherwise, we don't yet. And we might ask a second question and continue like this. And eventually, this is kind of the decision tree which would correspond to this algorithm. And we see that the query complexity in this case, it's the worst case. So here we asked 1 query, 2, and here we asked 3. So the query complexity in this case is 3. Is this clear to everyone? Are there? Okay, so just to quickly go through this, how we make this decision tree, we start off with the first query we ask, we make a child per answer, and we kind of consider it layered like this. We kind of keep going, and the sort of longest path from the root to a leaf, that's the query complexity, where in the leaf we always need to have one compatible edge set, like we saw on the slide before. Okay, so now a slightly more complicated definition that's also very important for this talk is what about randomized query complexity? So that's what I will be talking about. So a randomized algorithm, you can see it as just a probability distribution over algorithms. So you could kind of see it in two different ways. The first way is just at any point I can flip a coin to decide what my next query is going to be. But I could always have sort of gathered up all my coins together and bring them at the start. So at the very start, I can kind of flip all the coins that the algorithm will use. And after that, I just run a deterministic algorithm. So this is what the randomized algorithm is. It's just a probability distribution over decision trees. And now slightly more complicated is this randomized query complexity. So in this case, we still kind of see our input as just being a fixed graph. And for each fixed graph, we're going to be flipping our coins to decide what algorithm we run. And now what we measure is the expected number of queries on this particular input. So that's the sort of number of queries we want to measure. And now the randomized query complexity, again, it takes the worst case input for this measure. So for the people who just came in, just a quick recap. Whenever we get two vertices, we can ask a query which tells us the distance in the graph between these two vertices. And we've just been defining what it means to be query complexity. The query complexity is just the number of queries we ask on the worst case input. Okay, are there any questions so far about? Okay. So one possible randomized algorithm would be I just randomly order the vertices 1, 2, 3, and now I will query in order whatever vertex I named 1 to whatever vertex I named 2, and then if I need to, I still perform the other queries as I need. So can someone tell me what the randomized query complexity is of this algorithm? Sorry?
5 over 4.
Yeah, so you kind of expect it to maybe have gone down. So, but there's actually one case which it always takes 3 queries still. So our worst case input for the randomized query complexity is this graph here. And whatever we do, we take 3 queries before we've determined it. But if this graph would not be part of our graph class, then it would have been something a little bit more than 1, something between 1 and 2. So we need 1 query if we go here, and we need 2 queries if we had one of the other 2. It would be something like 5 over 3, or I don't know. Someone who can do calculations can compute that. But yeah, this is an example of what these things look like. Okay, so in fact, it could be that we're kind of unlucky, and even when we are allowed these sort of randomized algorithms, we might need to actually ask all the edges in the deterministic case, and in the randomized case, we might need to ask quite a lot of edges. So if we look at sort of this class of graph, we just have a single edge missing. If we think about the distance queries which would tell these graphs apart, it's only when we ask, in this case, the pair 2, 4, is when we find out that we're kind of looking at this graph and not one of the other graphs. So in principle, this seems like a bit of a silly problem, this distance reconstruction, because obviously we can do it always in n-squared queries for n the number of vertices in the graph, because we can just ask all the pairs, right? So this seems to determine it. And actually, this kind of problem kind of goes through even for quite restricted graphs. So even if we have trees and we have a vertex of very high degree, so this is a vertex which has lots of neighbors, and most of the vertices have 1 neighbor, but in one of the cases, one vertex has 2 neighbors, and in the other case, they all keep 1 neighbor. Then you can also look at the distance pairs, and again, there's only a small number of queries that are actually going to distinguish these 2 graphs. And you can show again, if you make a graph class from these, that you might need to ask order n-squared queries to reconstruct the graph in this case. So that's why in all the work so far, people have been bounding the maximum degree. And that's just if we don't bound this maximum degree, we have these kinds of bad examples, we have these kinds of bad examples, and we can't prove any sensible results. So for the rest of the talk, I'll have like deltas floating around, and that's just the maximum degree. It's just the maximum number of incident edges to a particular vertex. So I just wanted to run you through now a way that you can prove lower bounds. I think this is something that's nice to know in general. It's called the information theoretic lower bound. It's something that you can apply in lots of different settings. So in sort of computer science, we have lots of these conditional lower bounds where we maybe do like a hardness reduction, and we can say, assuming blah, 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 we now need this many time. But this is really nice because it actually gives you actual lower bounds, which in computer science is actually not that common. So if we would apply just this standard technique to our setting, I can show you what kind of bounds we get. So we can assume that, in our graph class we don't have too many possible distances. So for example, if the graph has diameter 4 or something, then there's only 4 or 5 possible distances. And that means that whenever we have a query, each query doesn't give too much information. It's just a number between 1 and 5. And that means that within Q queries, we actually can't distinguish too many graphs. Because when we've distinguished so if we've really distinguished the graph, then those two graphs need to have different answer profiles. Is this clear to everyone that when two graphs are distinguished, they need to have received different sort of bit strings of the responses onto the queries? Okay. And so we just need to make sure that there's many objects that we need to distinguish. And in fact, something that you can believe me on is that if you look at the number of graphs of maximum degree 10, say, then there's quite a lot of them, exponential n log n. And in fact, I can add on a little bound on the diameter as well. So for the people who know graphs, what you can do is you can take like a complete binary tree or something which has small diameter and kind of put that on your vertex set. And this will allow you to take shortcuts without really increasing the maximum degree of the graphs too much. Okay, so we have many graphs which don't have a lot of possible answers to the queries and bound at maximum degree. And what we saw is that each graph from here, if we want to reconstruct it, then it needs to have received a different response. So what we need is this exponential q log d. It needs to be at least exponential n log n. I can now put on my bound on d in here as well. And now I have something only involving q, which was the number of queries, and n. And from that I can get the lower bound. So this is just saying I need to receive enough information from my queries to tell apart the different objects that I'm needing to tell apart. And what we find is that the trivial lower bound in this case is n log n over log log n. Even when the graph has bound at maximum degree, we need to ask this many queries in any algorithm. Okay. I see some people nodding, so I'm hoping some people understood. Okay, so what our main result is that actually we improve on this trivial lower bound, and for trees we can actually determine very exactly what happens. So trees are kind of the most simple types of graphs you can think of. They're graphs on n vertices with n-1 edges that are connected. They don't have any cycles. We saw some examples of them before. And what we can show is that we can get rid of this log log n factor that we saw before. And more specifically, we can really tell you the dependence that delta needs to have as well. So I'll later also give you a matching upper bound on this, that on trees, we have an algorithm that needs delta n log delta n queries, and we also have this lower bound here, which is just a multiplicative constant factor away from our algorithm. And yeah, this is really for us the nicest result, because before the sort of best kind of lower bound was this type of bound. And so even for arbitrary graphs of maximum degree delta, this kind of bound was not known yet. And now for trees, we know very exactly what happens. So before I get into the lower bound, because that's actually a little bit more complicated, I wanted to focus this talk more on the sort of upper bound algorithm and tell you a little bit more also about what kind of things have been studied in this setting. So I just need one more definition here, which is about induced cycles. So cycles are things like this. This is a 5-cycle, a 4-cycle. And an induced cycle is just a cycle where there's no shortcuts anywhere. So these kinds of red edges, they're called chords, they're not allowed. Now, a graph is called chordal if all of its cycles are of length 3. And more general, we can call a graph k-chordal if we don't have any sort of large induced cycles. So all of our induced cycles, they have length at most k. So we don't have any sort of really long induced cycles like this. And what previously people studied for these bounded maximum degree graphs, they studied these kind of chordal graphs were one of the examples where they could do something for. So for general bounded maximum degree graphs, we're quite far from this n log n behavior. We still have n to the 3/2, and no improvement on this has been made. And we've tried actually quite a bit to improve on this n to the 3/2 just by an epsilon. And it seems actually quite difficult. But for some more special graph classes, people have been able to kind of improve on this. And this log to the 3 has since been improved to a log squared. And they also extended this chordal to 4 chordal. So now we do allow induced cycles of length 4, but no larger ones. And they were also the first to do deterministic things. So actually all of this work, they were all randomized algorithms. They had the first kind of deterministic algorithms for interval graphs, some kind of graph class that people know. And for chordal graphs, they couldn't quite do yet, but they could do a different problem called verification. So verification, for reconstruction, I want you to tell me what the graph is. For verification, I tell you, oh, I claim that it's this particular graph. You just need to check if it's this particular graph, yes or no. So it's a slightly easier problem. So what we did is that we shaved off this sort of remaining log factor on the algorithmic side, and we can extend it to any k-chordal graph, so it still has some assumption on how large induced cycles we can have in the graph, but we sort of push this a bit further. And also on trees, we get something really specific. So this is the bound that I was claiming to you before, that we can, this big O, I was sort of hiding dependencies on delta and k in there. And also our algorithm is actually deterministic and so simple that I can show it to you during this talk, and that hopefully like at least 70% of you will feel very confident with it, and quite a few of you will feel somewhat confident with it. So it's really nice that it actually got a bit simpler as well. And it's quite once you see it, it's quite a silly algorithm. So I invite you to now think about how you would actually do this on the tree. And once you see it, you kind of go, but this was really stupid and easy. But coming up with it clearly was a bit more difficult. Are there any questions about the main result, that main algorithmic result? Okay. So maybe I'll skip over some of these. So what previous work, just wanted to say a little bit about what previous work did and why it's sensible to do sort of randomized approaches. And that's basically because, at least for the chordal case graph, maybe I'll tell you a little bit about that. There's a notion of a so-called balance separator. So people in structural graph theory, if you've been attending all these talks, you will probably have seen this type of picture before. A balance separator of a graph is a set of vertices that when I take it out, I reduce the size of my graph by a factor of 1/2. So the remaining components, they don't have any edges between them. There might be some edges going to the separator vertex set. And the reason why algorithmically these balance separators are very nice is that I can keep breaking my graphs further into components and components. And if I do something for this separator, and now my component size has reduced by a factor of 1/2, and now I do something here again, I know that I will have to repeat at most log n times, because each time I've reduced my instance size by a factor of 1/2. So if I repeat log n times, then I've sort of reached something very small where I can brute force. So that's a reason why these things are very nice to have. And in the randomized case, actually, what people did was that they have had a nice randomized algorithm for finding a good separator. So they didn't know how to directly find this, but what they did is that they kind of noticed that if you have a vertex that lies on many shortest paths between other vertices, then the neighborhood somehow is a really good separator with high probability. And that's what they used to find such a separator. So what they did is they take 2 random sets and they query the distances there, and then they try to figure out which vertices lie on many shortest paths to get such a separator and then do something with this. And the sort of main thing that we changed in our algorithm is that we actually have a deterministic approach to finding these separators. So just to repeat, what we show is that we start off with a graph which is a tree, and we have maximum degree delta, we have n vertices, and this is the number of queries that I'll allow myself. So the first thing that I'll do is that I will ask all the queries. I pick my favorite vertex of the graph and I ask all the queries to all the other vertices. So this is just n queries that I've done so far. And this roughly partitions my graph into different layers. So this is sometimes called a breadth first search layering. So here I've put all the vertices with distance 1 to this vertex, all the vertices with distance 2, etc. And this already tells me a couple of edges here. And it also tells me a couple of non-edges. So when layers are sort of 2 apart, they can't have any edges between them. And I also know that each vertex here has exactly one neighbor in the layer above it, because it's a tree, so it can't have multiple vertices in the layer above it, because it always has a path via the vertex 1. So I don't know where these edges are, I just need to find that out. So I'm going to assume inductively that I've reconstructed the first few layers. I've just asked some questions, and for the first few layers I actually know what all the edges look like. And the only thing that I'm going to do now is for each vertex here, I'm going to find out which of the vertices in the layer above it is adjacent to. So note also that within a layer there also can't be any edges, because for the same reason the graph wouldn't be a tree, we would create a cycle. Okay. So what I'm going to do is I'm going to pick a special vertex. I've indicated it here in red. And I'm going to query from my vertex. I'm going to query to all the neighbors of my special vertex. And in fact, it will always be the case that for one of them, it will really be the closest vertex. Because this vertex has a parent somewhere, and it has a way to get to the red vertex. And to all the other vertices, it will always need to take 2 more steps. It will need to step to the red vertex and then go there. And this is using, again, that in trees, between any 2 vertices, there's like a unique path between them. So we know that among these neighbors, we're going to hear some responses, and one of them is just going to be the smallest. And now what does that tell us? It tells us now where the parent of this vertex must be. So initially, this could have been a parent of this vertex. It could have sort of been in this part of the tree. But now we know it's not the case, because then this number would have been lower. So we know that the parent of this vertex needs to be on sort of this side of the graph. But now we can, of course, repeat the same idea. We can pick a new vertex in the area that we still were searching through, and we can again query all the neighbors. And again, we will have this situation that say that my parent was A, then this distance will be 2, and the other distances will be 4. So from sort of the neighbor of this vertex with the smallest distance, I know that the parent needs to be in the subtree below that vertex. So this is what the algorithm does. It somehow has a way of picking these vertices. And of course, we want to pick these vertices a bit cleverly, so that we don't have to repeat this step too many times. Because each time that I do this step, I maybe ask the max degree number of queries. But I will eventually find this vertex which has a lower number, and then I will be able to go to a smaller component. So here I just say that I remove some of these things. So now the really key property here is that I can always pick this vertex to be a separator, balanced separator, in the sense that the remaining subtrees, they keep reducing the instance size by a half. And that's because, remember that we assumed that we already knew how all of this looked like. So this has a certain size, maybe 100, and I can now pick a vertex in that subtree that I've reconstructed so far that splits all the other parts into something of size at most 50. And now after that, I can repeat the same thing on the thing here, which splits everything into size at most 25, etc. So I'm just going to kind of like binary search where the parent of this vertex is. I'm sort of going to the tree above, and I'm kind of going to binary search through it where the parent is. So this is the whole algorithm. We do a BFS layering. It's n queries. For every layer, for every vertex on the layer, I find the parent. And as I mentioned before, if we keep doing these half-balanced separators, we only need log 2n rounds. And each round takes delta queries. So the number of queries I've used now is n times delta log n queries. So are there any questions about this algorithm? Is anyone unhappy with anything I did so far? Or?
So verticity query might not be at the top level. It can be at the first verticity query at the upper part. It might be not at the top. It might be whatever separator is. It might be whatever layer.
Yeah, it could be anywhere. So I had quite finite space on my graph here, and probably, I mean, I'm not sure what would have been a balanced separator actually in this picture. It might have been actually that this would have been the first vertex that gets chosen as balanced separator, and then these vertices would have been queried. Yeah. Yeah.
Do you know the separators in advance?
Well, yeah, so you could compute all these separators. In principle, you can compute all of them given this tree in advance if you like. But of course, this tree will keep changing once we go layer and layer. But you can kind of query them on a need-to-know basis, I guess. Find them on a need-to-know basis. And of course, you can actually, so in this query reconstruction setup, we usually don't care about efficiency at all. So we can do sort of infinite computation. It's more about how many questions do we need to ask. But this actually is pretty efficient also, finding these vertices. Yeah. In the tree, yeah. Yeah, so actually there's something you should still be a little bit unhappy about. I don't know if someone spotted very precisely. I didn't quite prove yet what I promised you to prove. Maybe someone has spotted it. So actually what I promised you to prove was there's still a little delta here at the bottom. So I mentioned to you that I was very proud of the fact that we got really the exact correct dependence on delta, and we actually put in some effort, quite a lot of effort on the lower bound side to get in this delta. And on the upper bound side, we also need to put in a little bit of extra effort to get in this delta. That's very much maybe a mathematician thing to do, but we were kind of unhappy yet with not getting this delta dependency on here. And it's actually not too bad. So if we wanted to get the delta in there, we need to make sure that we don't just query all the neighbors of a separator. So we need to be a little bit more clever and make sure that we don't query all the neighbors all the time. So what we will do is we will take our separator, it will split the graph into some components. We order these components by size, and we do the very natural thing of first asking the neighbors with the largest component sizes. Because if we learn the sort of shortest distance was something with a large component size, then we made sort of less progress because our graph only shrunk by a little bit. But if we have to ask many queries, we eventually reach we know that we asked, say, 100 queries. Now we're also sure that our component size has reduced by really a factor of 100 and not just by a factor of 2. And if you do the calculations for this, then this is actually the number of queries you end up with. And funnily enough, so in this talk before, as I was saying, we have these randomized and these deterministic. And what we actually show is we have this deterministic algorithm and we have a randomized lower bound. So it kind of seems to show randomization doesn't help. But I would conjecture that randomization still helps. And I don't see anything better that I can do here to get 0.9 times this. But I can do that if I'm allowed randomization. So you could do the same type of algorithm, and instead of doing this ordering by component size, you could pick which vertex you're going to ask first randomly, where you pick your probabilities proportional to these component sizes, and that actually shaves off an extra half here. So that's kind of curious. I don't really know. I don't know a deterministic lower bound which really has this 1 here or something larger than a half. So I don't know if this is really the case that randomization does help a little bit, but it seems to help a little bit at least. At least here I can't do better deterministically than putting a 1 there, and randomly I can put a half, approximately. So that's just, again, some calculation that you need to do that I will sweep under the rug. Okay. Are there any questions about this? Yeah, so as I mentioned, we have this type of other graphs that we can extend to. And for that, we use the same kind of approach. So we again do this sort of breadth first search layering, we inductively reconstruct something, and we again try to find the neighbors in the layer above you via some kind of binary searching. But there's a couple of difficulties. So before we only had one neighbor in the layer above, now we might have several. That's not so much of an issue. But we might also have neighbors in the same layer. That's also still not so much of an issue. But the most annoying thing actually is that this thing that I showed you, the same algorithm, doesn't directly work. So before we knew that we just picked this separating vertex, we look at whatever vertex was closest to our parent, and that's the component we need to go to. And this is no longer the case. So you could look at the closest neighbor of this separator, and it's no longer the case that your neighbors are necessarily in that component. So you need to adjust the algorithm a little bit, but the same overall kind of idea works for more graphs. And I just wanted to show you a little bit of a glimpse of what these algorithms look like. I guess this will be more of these kind of structural talks that you might have seen before. So this is just to handle the case where we might have two vertices in the same layer, and we want to find out whether they have an edge between them. But we have this sort of special property that we prove that when two vertices in the same layer have an edge between them, then their neighbors, which maybe we've been able to find already, they need to be quite close to each other in the graph above us. And this is a really nice property, because if we have this property, then say we don't know yet these edges, but we know these neighbors. So to find out what vertices this is adjacent to, I just look at its neighbors. There's only delta of them for some constant delta. And they need to have a small distance with respect to these neighbors. So there's at most delta to some power of them. It's still some kind of constant. And I only need to just ask those queries. So these are the kind of sort of structural claims we get. And the reason why these induced cycles come in here is very easy to see in this particular case. So we could look at a particular instance where we have two vertices next to each other on the same layer, where we do have a very long path, which is the shortest path from u prime to v prime in the graph above here. So that means that there's no shortcuts here. We don't have any edges there. So this is very dangerous of becoming one of these induced cycles that we were not allowed to have. So this is a very, very long cycle, much longer than the length of induced cycle that we're allowing. So we need to make some shortcuts. We can't put any shortcuts here because it's the shortest path here. So the shortcuts need to be from u and v to something on this path. So we could still have these types of edges. But we can't have too many of these edges because these vertices have bounded degree. So the number of such edges can be at most 2 delta. So if this thing is really, really gigantic, then somewhere we're getting one of these induced cycles that we were assuming were not in our graph. So this is really one of the things where you can see where we really specifically use this no long induced cycles property, where we can get some kind of nice structures out of. So those are the type of arguments that go into this k-chordal case, and the rest is, it's a bit longer, the proof. But this is kind of what these things look like. Okay, so I also wanted to say a little bit about our lower bound. So as I mentioned, that we were kind of happy to really get this dependency on delta as well. So you can think of delta as a function growing with n, but I'm lying there a little bit because it's not allowed to grow very quickly with n. But yeah, for some ranges we're able to handle them, and definitely something like log n works, but it depends a bit on the values of n, how many deltas we can actually handle. But this always works. So in this lower bound, we need to show that whenever we have an algorithm, we need to use many queries, not just for deterministic algorithms, but also for randomized algorithms. And actually, one of the first ideas that goes into this is that we'll further make our life a little bit more difficult in some ways by not just considering all trees, but a smaller class of trees. But this also makes our life a little bit easier in the sense that this is kind of the idea of sort of removing some noise. There's some bits of the trees that we don't actually care about. So maybe those trees we just don't consider to begin with. And if we think about our algorithm and when it really needed to take a lot of time, in the first few layers, it doesn't really matter what it does, because I mean, the first few layers is just a relatively small tree, so it's never going to contribute many queries. The most queries is actually at the very last step of finding the parents for the leaves. So if we, for example, took a complete delta array tree, so maybe I'll just draw a little picture what these things look like. So these are these kinds of things. If we take such a graph, then actually the algorithm takes the most time that if it has a vertex here and it needs to figure out which of these things are its parent. That's where actually most of the queries are used. So what we're going to do is we're going to assume that we're only going to be considering trees that look like this. We're going to tell you exactly already what the names are of these vertices. And you just need to figure out, tell me the names of all of these vertices. So a different way of drawing it is I've labeled them in a particular way here. I might call the root of the tree the empty set. Then here I've called this vertex 1, this vertex 1, 1, 1, 2, 1, 3. Just sort of labeling the edges that I took to the top. And I've actually added a little bit on top of my binary tree. That will just be easier for analysis. At the very leaves, I just add one more leaf each. And so the only thing that I need now, I will also tell you the names of these. Whatever. And the only thing you need to figure out is how these sort of remaining vertices, how they distribute themselves here. And so what we actually get is we have a sort of function reconstruction problem where we have a collection of elements and each of them has a parent. So this may be phi1, maybe it turns out that its parent is 1, 1, maybe it's the vertex that's here. And this is really a bijection. So each vertex here has exactly one of these things as its parent. So this is sort of a reformulation of our problem. And now we have to think about what distance queries tell us. So distance queries between vertices here don't tell us anything new. We already know the answer. The thing that tells us something new is if we query something from here to here or from here to here, these kinds of queries. So let's have a look. So let's say phi1 at parent 1, 1, so it's over here, and phi2 as parent 3, 3, so it's here. And we ask this query. In this case, we hear the answer that we basically hear that this is the lowest common ancestor. So what do we hear? The distance is twice because we will walk up and then we will walk the same amount down. We have a 1 because we always need to walk to the parent. And then we hear 2. And 2 is just the position of our nearest common ancestor, not exactly which one it is, but just on which layer it is. So this is what we hear, and I can do a different example as well. If we did phi3, and maybe phi3 was over here, and we ask this query, now we will hear 2 times 1 plus 1. And this 1 is, again, this relevant bit of information that we actually learn about, is just on which layer is the nearest common ancestor of these two vertices. And in terms of sort of the bit strings that we've assigned to them, what we actually learn is if we had the vertex 1, 2, and 1, 1, we heard the answer 1. If we had 3, 3, and 1, 1, we heard the answer 2. And actually, you want to think about this in the opposite way. So you kind of want to see this as 2, 1, minus 2, and this one is 2 minus 2 is 0. And then it tells us how many of these first things that it has, how many of the sort of elements in my bit string it has in common. So I've repeated that on this slide. So maybe if I would have asked, for example, these two vertices, what I learn exactly is that the first 3 things are the same. I don't know if they're 1, 1, 1. I just know that between these two vertices, they have the same numbers there. That's exactly the information that we learn. So I've just repeated that here. We have some sort of unknown bijection. These are sort of these leaf vertices. I've just replaced the 3 now with a delta and the size 2 with a k. And the oracle answers the smallest index I for which they're different. So we kind of hear, okay, the first 3 are the same, and after that, at some point, they become different. That's exactly what we hear. Okay, so this is sort of a new oracle that we invented that might be of independent interest. And from there, we actually go to a slightly different oracle, because something which is a little bit annoying here is that we don't get yes-no responses. And it will be much easier to analyze something with yes-no responses. So something that we can think of as well is that maybe we can get two of these strings, and we can tell you an index 2, and we just hear whether these two things are the same or not. And surely this oracle has become in some ways more powerful, because if I use this oracle, I can use it to simulate that oracle. So what can I do if I want to find this out? I just start asking 1, 2, 3, etc. until I hear the answer no. So I have asked more queries here, but for each query that I do here, I only need a single no answer in this thing. And what I'm going to be doing is that we have sort of oracle 1 and oracle 2, and here we have number of queries. And I'm going to link it here to the number of no answers. Yeah. So this was the oracle that we had. There's actually, I've sort of been slightly lying. There's one other type of query that we need to allow. Yeah.
Could you do binary search with oracle 2?
Can you do binary search with oracle 2? Yeah. So yeah, you can really simulate. This kind of. You can use oracle 2 to simulate oracle 1. So it's at least as strong. But in principle, I mean, you can't. To go from oracle 1 to oracle 2, it's a little bit more tricky potentially. But the thing that I will need, so I want to prove a lower bound for oracle 1. So if I make oracle 1 stronger, then that is fine. So what I'm going to be showing is that these two things are kind of linked, so that if I want to say I lower bound this, then I also get the lower bounds. If I can lower bound the number of no answers that oracle 2 must always hear, I also get the lower bound for the number of queries that oracle 1 must always do. But indeed, you could also use, maybe you could also use oracle 1 to somehow simulate this in some ways, but it seems a bit more tricky because you don't want, yeah, you ask one query here and you immediately learn a lot of oracle 2 things, so it's, yeah, this oracle is stronger in some ways, but yeah, in this kind of way, it's not so much stronger. So this is what I wrote down. We have this sort of new kind of oracle which does these kinds of queries. And to lower bound the number of distance queries, I'm going to lower bound the oracle 1 queries. And I'm going to do that by lower bounding the number of no queries for this new oracle. And there's one small other caveat that I put in here. So here I kind of was reasoning about queries where I was asking between vertices that I wanted to place. And as I mentioned, we could have also asked a query from a vertex here to a vertex here, for example. And that will give you a slightly different types of dynamic. So that's why there's also a sort of second type of question that the oracle is allowed to ask. But you can ignore that. It's not too important. Okay. So maybe one sort of final idea slide that I will give on what we can do with lower bounds is that if we want to prove deterministic lower bounds, then the common approach is something called the adversary method. We kind of take our worst case input and or we take our algorithm, and as we read our algorithm, we're going to construct to you a worst case input. And that's something that typically doesn't work for randomized algorithms because we don't have a fixed algorithm. So yeah, the input, there might always be some positive probability for an algorithm that works well on the input. And instead, something that you can do for randomized lower bound is something called Shaw's minimax principle. And what it essentially does is that it allows you to think about the deterministic algorithms again, but now on randomized input. So you could say that it moves sort of the randomness from the algorithms to the input. And instead, we're allowed to look at the following question. We sample a uniformly random bijection, a function like this. We sample this uniformly at random. How many queries does a deterministic algorithm need? And this sort of, yeah, so this sort of worst case probability distribution on inputs. So if we, so we can kind of, if you would really take the worst case distribution, then it would be an equality. But again, because we're just proving a lower bound, I can pick you a distribution which turns out to give a good lower bound. So the fact that I'd used the uniform random distribution here, I could have used a different distribution as well. It's just about what I can prove for it. And for this particular case, I can prove that on a uniformly random input, actually a deterministic algorithm needs many queries. And that will show to you that any randomized algorithm has a high randomized query complexity. So if you ever need to do something like this, then this is quite a useful first step. And now a second sort of nice idea that goes into this is that this sort of bijection is very annoying because a bijection, it has all kinds of dependencies. If I figure out one of the coordinates, if I figure out some of the coordinates already, then the remaining coordinates are no longer independent. There's some things that they already can't go to. It's much nicer if it's just a uniformly random function, because now all the queries are independent. They can just, these things are all sort of sampled like that. And in the case where we just look at uniform random functions, we actually can use Chernoff bounds and these kinds of things to look at how many queries we need to do and show that with really gigantic probability, we will need to do quite a lot of queries. And this probability is so large that it really dominates the probability of it being a bijection. So you could see it as, these are sort of the functions on which we need many queries. There's like a tiny fraction of functions on which we might need a lot of queries, and this is the number of bijections. So then we also know that there's only a small fraction of the bijections on which we need many queries. So this is one other sort of nice idea that goes into this proof, that you can disregard some of these things. But this is really like the sort of core technical details of our paper is, yeah, proving these kinds of concentration bounds. Yeah, so let me maybe skip over some of this. There's also some other settings that our algorithm applies to. So there were some other types of things that people studied. So some of these things that are listed here are really very much the same thing as we did. But one other nice setting that people looked at is a so-called partition reconstruction problem, where we have a bunch of items, and what we can do is membership queries. So we can ask, are these two items in the same part, yes or no? So for some of these questions, we also sort of broke through this sort of information theoretic barrier. So they already had, so for example, for this one, they already had some kind of lower bound in terms of the number of items and the number of parts coming from this counting argument. And then we can really give something tight. And for all of these settings, actually, they quoted this, they quoted some kind of lower bound for this, and they had already the matching algorithms. But they couldn't quite do the lower bounds there yet. So that's also something quite nice. So people have studied these kinds of things from all kinds of different viewpoints. To mention at the end, I just wanted to mention some nice open problems. So I mentioned that we've been looking at these sort of more restricted classes of graphs, so trees for the lower bound, k-chordal graphs for the algorithm. But I think really one of the nice open problems here is doing better than this 3/2 for general maximum degree graphs. So just shaving off an epsilon would already be nice. And these k-chordal graphs that I looked at, they had this property of having small separators, of being able to do this general approach. But they have a little bit more. They also don't have these long induced cycles, and we definitely needed that in a bunch of places. So there's this notion of tree width, which just says that you can always find these small separators, and just that is not enough. So we're not able to break through this barrier, even for graphs of bounded tree width or planar graphs, which means that you can draw them on a plane without any intersecting edges. And yeah, something else that I think would be interesting is to prove a better lower bound for general maximum degree graphs. So for trees, we have this delta log delta n type of algorithm. And it could be that just for all maximum degree graphs, we have such an algorithm. So it'd be very nice to even get a deterministic lower bound of this kind of form, just to separate out trees from other maximum degree graphs. And of course, yeah, our proof, yeah, it's really only using trees. So maybe by considering more graphs, you can prove a better lower bound. And also the thing that I mentioned before, that we've kind of been looking at this this deterministic and randomized query complexity. We got it into this form, but it could be that a better constant is possible by randomization. This was something that I mentioned before, so maybe there's this type of lower bounds for deterministic algorithms. It could be that even this thing that we reached, it could be that this is really basically optimal. It could be 1 minus epsilon times that. But I think breaking through this a half would be nice, just to separate out the randomized and the deterministic here. Yeah, so I'll just end my talk on that, and thank you very much for your attention.
It's a great talk, thanks a lot. Are there any questions? If there are questions, please wait until you have passed your mic so that we get it recorded. Questions? Okay, maybe I'll start. Is it, I don't know, maybe it's a silly question, but if I allow you, for example, to make mistakes in reconstructing the graph, let us say some portion of the graph will be wrong, so you got almost everything correctly, up to some mistakes, like some edges are not really there, some edges are there, but you did not identify them. Do such variants, make sense, or as a study?
Yeah, so usually people actually ask the opposite problem. What if you already know it up to this, can you figure out the rest? Because actually, this example with the cliques showed that even if there's just one edge missing, it might be difficult to find the missing edge, right? So it's definitely the case that there's still a hard bit of work left after you've figured out most of the graph. But I don't know if it would be easy to get an approximation. I think it's a little bit, I think this would still be relatively tricky in most cases. I don't think this has been studied much of getting really such an approximation, but I mean, it also depends on how approximate you're allowed to be, I guess.
Correct,
yeah.
Yeah,
there's that.
Can you make any ideas here apply to a continuous setting? I mean, if you just have a metric space and you've got pairs of points and you can ask the distance.
Yeah. And now you want to, what kind of metric spaces do you allow to start off with? Because
I don't know. I'm kind of thinking of a topographic map where you've got uphill and downhill and you're,
Because you need to make sure, I mean, if you have a discrete set of answers, and then of course it's going to be always a bit silly, because if there's lots of different types of metric spaces you can start out from, you might always need to ask a lot of questions, I guess. Mm-hmm. But yeah, it would become quite a different realm of possibilities. It would very much require you to study the structure of those things, because I imagine that in this case you also want to have distance queries which give you back a real number or something. Mm-hmm. So it would very much give different types of argumentation, I imagine. Yeah. So people have studied, there's limited amount of work on reconstruction problems which are in continuous settings. So I think, for example, points in real lines, and not this kind of distance, not query reconstruction, but normal reconstruction, where you learn the distances between the points. Can you find out how they're configured in space and things like this? You could, or how many distances do you need to determine the points? Those kinds of questions have definitely been studied. But I don't know about figuring out what type of metric space it is. Then you also need to start off with a classification of what is possible, I guess.
Thanks. Is there any last question? If no, let us speak again.